Hi, I'm Max, a research fellow at the Center for Healthy Longevity at the National University of Singapore. I work on one question: what controls maximum lifespan and how can we change it? I'm a theoretician and I model my day-to-day after gentleman scientists from the Victorian era. I think, I write, I drink coffee or tea, I take long strolls to ponder problems, and I meet people to discuss ideas. Come, let me show you one of my latest thoughts that I have. So what I'm really interested in is what controls maximum lifespan. And why is it that certain large animals like whales or as humans can live for centuries, whereas other short-lived animals like rodents, your mice and your rats can only live for a few years. And we know that allometric scaling laws, that lifespan roughly scales at the power of 1/4 of the mass. And what I'm particularly interested in is what are those deviations? We know this gives you a rough idea, but really, what explains this part here? What explains the difference between the actually point of the animal or the species and the theoretical allometric scaling line? Just now I was telling you that different animals of different sizes have different lifespans. And the way I've been thinking about it is, what is actually happening at a very cellular and molecular level, and trying to derive maybe those lifespan rules from there. And if you think about it, if you have a cell in your body, right? It's in this 37-degree temperature in this wet environment, and just due to basic physics, you always have thermal fluctuations, right? And even if the cell is doing nothing, right? It's just sitting there, you always have thermal kicks that does something to the cell, right? And those thermal kicks, they induce pore openings, so certain ions flow in. And for the cell, trying to stay alive, even if it does nothing else, it always has to try to pump those ions out again, right? All those intruders that go in, it has to pump them out again. It has to keep the membrane potential. And this is just when it's dormant. But of course, a normal cell does other things, right? It does things like defending against infections, right? You might have getting some viruses in there that try to do things, right? To the cell. The cell is also of course trying to reproduce and doing all those other metabolic processes, and not only just trying to survive. So, and all this costs energy. All this has to do that the cell has to maintain itself and creates a basic minimum requirement for the cell. Now the issue is, if the cell wants to reproduce, right, it wants to double itself, then it also needs energy for this doubling, for reproducing, for self-replication. And in a way, this is where you start having certain constraints that fight with each other, and that all the energy that the cell uses for reproduction cannot be used for its maintenance. And through that, you slowly get a less maintained and maintained cell, and therefore you get damage that accumulates, which eventually leads to aging. And how those two things connect is that my current calculations show that this delta between the human and this line is mainly given to those energetic constraints that animals that live much longer for their body mass are just better at distributing this energy accurately, and therefore are able to maintain themselves better and therefore live longer.
That's it from me. If any of this sparked any questions, big or small, please drop it in the chat. I'll be moderating the Q&A later, and I'd love to pull your questions into the discussion. You can also follow me on X at Max Unfried, like unfried chicken, for spicy takes on longevity and updates on physics. Thanks, See you in the session.